Welcome everybody. This is lecture 4. And today's topic is about discrete empirical interpolation method, which will be short DEIM. Okay. So I also want to mention that in the lecture notes you will find all the references. I'm not really talking about references in these lectures, but in the notes you will find the references if you want to learn more. Or of course, always feel free to contact me if you have some questions. Okay. Okay. So as I mentioned in the previous class, let's again take a look at the reduced model. And I will define capital FL of T, YL of T as psi transpose F T psi YL of T. Okay. So what it's clear is that although this is an L-dimensional vector, this is not independent from the I-dimensional problem. So this is in RD. So what we want to achieve, so you see what we do, we have to expand to the high-dimensional problem, evaluate F, and then project. So here what we have, this is L by D times 1. Okay, but each iteration, this might be very expensive because we have to, still get back to the high-dimensional problem, and also to compute each iteration, we have to compute the perturbation. So this step cannot be offline. So each iteration we have to update and project. So this is for sure very expensive. Therefore, what we propose is to approximate F T psi YL of T, this form, as some orthonormal matrix times C of T. In other words, we want to write as a linear combination of CIT, Phi, I goes from 1 to K. So phi are called empirical basis. Okay, and so we want to make an interpolation onto some empirical basis times some coefficient that we have to determine. So C of T is going to a function from 0 to capital T with values in in our K. So eventually K is way more than the original dimension. Okay. First step is how can we compute phi? So imagine that we have already set the low dimensional problem So this implies that we have already computed snapshots yt0, ytn. Okay, in order to compute the empirical basis, why do they are called empirical? Because those are going to depend from the snapshots. The empirical basis, we set the snapshots for the nonlinear, the snapshots for the nonlinear, I would say the snapshots metrics for the nonlinear terms. And I would say this is n, so n is going to be the matrix. And now this is f evaluated in t0, y of t0, up to f of t0, y of, sorry, this is tm, y of tm. So again, this is a matrix now, which is dm minus 1. And so now this is just an evaluation on the snapshots, which are the expensive part, evaluated in the nonlinear term. And to compute and the phi are, so phi i's are going to be the POD basis of rank k in this case for n. So now the basis, the empirical basis, are computing upon the snapshots of the nonlinear terms. Okay. Then, so now we know how to compute. So I recall that what we have phi of t, f of t psi yl should be approximated by phi c of t. Okay, I can multiply on the left by a matrix pt pt, where p is a matrix which is in d by k, and that considers k columns of the d by d permutation matrix. So in other words, we have a permutation matrix, and we consider the first k columns, Now, let me go. So let's consider that we have P transpose F T psi YL of T, P transpose phi C of T. If P transpose phi, which is a matrix K by K, is non-singular, we obtain C of T can be P transpose phi inverse P transpose F of T psi YL of T. So this should be true. So P transpose phi should be non-singular. What does it mean? What does it mean to compute, for instance, what is the meaning of P transpose phi? So imagine that so this means that we are selecting, we select k rows of phi. The same is for where we select k rows of f. Okay. So in the literature there are works to say how we compute P, and we select the rows. So one can use an greedy algorithm, something like an LU decomposition. One can use a QR with pivoting algorithm. So nevertheless, the interesting thing is that we are selecting rows of the nonlinearity. By the way, this is still expensive. Why? This is still expensive because we still are linked to the high-dimensional problem. But if we can plug P inside the nonlinearity, so that means that P transpose F of T psi YL of T is equal to F T P transpose psi YL of T. What does it mean? This is going to be K by D, D by L, L by 1. So now this is going to be a vector in Rk with K less or way smaller than D. Okay, now we are somehow in business. So that means that we do not evaluate F everywhere, but just in K selected rows. Is that reasonable? Or when one can plug the permutation matrix, I mean the selected columns of the permutation matrix inside F. For instance, if F can be evaluated component-wise, this is possible. So each line is independent from the other, and then we can do that. So that means what we have a DIM approximation or DIM approximation of F T Y of T, which follows. So here we're gonna have F T Y of T. I'm going to call F L K. So L are the number of POD bases, K are the number of DIM bases. Okay, T Y L of T. This is going to be phi P transpose phi inverse f of t p transpose psi yl of t. So I recall that here we have used that C of t is given by this form, but I also recall that our assumption is that f is given by phi times c. This is the reason that here we get a 5 and p transpose. Okay. So this is quite interesting now. So let's check here. We have phi is a matrix which is, what is the dimension of phi? This is d by k, k by k, and this is going to be k. Okay, that's what we want, because f should be something dimension d by k. Okay, let's also check all the quantities here. The quantities here, for instance, p transpose phi inverse, this is a matrix which is k by k. Also, we have p transpose psi. This is a matrix which is in dimension. This is going to be k by l. Those quantities can be pre-computed. Okay. So let's take a look. Here we started with a problem, high-dimensional problem. A y of t plus f t y of t y of 0 equal y0. Okay, then we have the POD Galerkin, which reads as ml y dot t equal a yl of t plus psi transpose f t psi yl of t, and then we also have, this is yl of 0 equal psi transpose of y0. Okay, then we can make a further reduction, and what we are going to get is something like ml y dot l of t equal al yl of t psi transpose, and then we use the approximation of phi of f. So this is going to be phi transpose phi inverse. Then we have f evaluating t p transpose psi yl of t. And here again we have yl of 0 psi t y0. So this is what is the so-called POD DIM approximation. Of course, so POD DIM is a further approximation of the POD Galerkin approximation. So we cannot expect that the error here is better than the POD error, but what we can expect is that we are computationally faster. So there is always a trade-off between accuracy and computational efficiency. So why here this should be more efficient? So let's go to the next slide. Again, I'm going to rewrite the POD dime. So this is going to be ML y dot L of t, A L y L of t, plus psi transpose phi P transpose phi inverse F of t, P transpose psi YL of t plus initial condition. Okay, here, so here the first, so here we know that that depends just on the dimension L. This is as well here. Now we have psi transpose phi, which is dimension. This is L by D, and this is D by K. So this is a matrix of dimension L by K. Then we have that P transpose phi minus 1. This is dimension K by K. And then we have, of course, we have the P transpose psi. This is dimension K by L. So all the quantities do not depend from D, the original dimension of the problem. Okay. So let's also check here. This is a vector in RL. You never go to the original dimension. So we exactly get what we wanted, something which is completely independent from the high-dimensional problem. So what I also want to mention is how to compute P. So I can shortly give an algorithm for dime or DAM. So what are the inputs? The inputs are the snapshots. So the matrix D times M plus 1. And the number of DIM. What is going to be the output? The output is going to be phi and P. So at the beginning, we need to compute POD basis of rank K for N. Then we compute QR with pivoting. Such that P tilde P is equal to QR. And then we store the first k columns of P tilde into P. So all this business, what we need to do, we need to compute the basis for the nonlinear term and some columns of the permutation matrix. Then what we also need to compute are P transpose psi, P transpose phi inverse. Actually, we never compute the inverse here. And we need to compute psi transpose phi. Those quantities are all independent from the dimension n. Okay. What is left to mention is how do we approximate the problem. So if I get again the POD dime approximation, AL YL of T plus psi transpose phi P transpose phi inverse F T P transpose psi YL of T. So if we use an implicit scheme, our function that we want to solve is going to be M L X minus Y, let's call Yj now, minus delta T times AL X plus psi transpose phi P transpose phi inverse F T P transpose psi YL. This should be equal to 0. So we are going to use a Newton method, and the Jacobian of FLK in X is going to be ML minus delta T times AL plus C transpose phi P transpose phi inverse Jacobian of F computing T P transpose psi X. Sorry, this should be X times on the right P transpose psi. So now this is how the Jacobian look like. And then once you provide F and the Jacobian of calligraphic F, FLK, we can again use the Newton method. Okay. So I want to stress that we are interested in computational efficiency, but also in accuracy. So, I mean, of course, we can be as fast as we want, but if the results are far from the original results, I mean, this makes no sense. For the DIM approximation, we have an error estimate So at time t between 0, capital T, the error between f of t, y of t, and its DIM approximation that I'm going to call FLK T YL of T is given by the norm of F T Y of T minus FL K T YL of T, which is less or equal some constant C tilde identity minus phi transpose times F T Y of T. I can consider the two norms here, where C tilde, this is equal to the norm of P transpose 5 inverse, and this value depends on the method used to compute P. It was actually proven that P coming from a QR decomposition with pivoting is more stable. And the term, the matrix identity minus phi transpose, this measure the projection error. Applied to F T Y of T. So it is known that phi transpose phi, that gives the identity. It's a K by K matrix. Phi transpose, this is a D by D matrix, and that is not the identity. Okay. I actually have still 10 minutes, so maybe it's interesting to do a step back and to think about a 2D case and approximation of a 2D case. So let's consider that is something that we are going to use in the next lecture. Find this one for 2D parabolic problem. So we consider y tilde t ct Laplacian of y ct with some coefficient plus f t y tilde c t. Zero capital T. Then we have an initial condition y tilde c 0 y0 x, and then there is at the border. At the border, we have that ct is equal 0. C is in the border omega. If we what we need to approximate is the Laplace operator. So I'm going to use the notation. So we have to discretize the space. So for instance, omega is going to be a rectangle. Okay. C is given by, it's a two-dimensional vectors, C1, C2. And so we choose delta C fixed for both dimensions. And also we use the notation Cij to define the I component of the first variable of Ci and the j component of the second variable. So if I want to approximate the Laplace operator of a function y c ij at time tk, this is a 5 points, well-known 5 points approximation, and this is actually given by yi minus 1 j time k minus twice yijk plus yi plus 1 j. So this is in the I direction, so in the first variable. This is delta c square plus yij minus 1k minus 2 yijk plus, this is a k, I j plus 1k delta c square. So with compact notation, we can actually define a matrix A which is 1 over delta c square, given by a matrix which is still a three diagonal matrix, but this is blocked. So we have T identity. I'm going to define the matrix T in a Y. So this is E, I, and T, where the matrix T is given by three diagonal matrix minus 4, 1, 1, minus 4, 1, and so on. So in this way, so what we have that I and T, those are matrices of dimension n minus 2 times n minus 2, and A is going to be dimension n minus 2 square times n minus 2 square. This implies that the dimension D of the problem is actually n minus 2 square. So you see, the higher the dimension of the PDE, the higher the dimension of the discretized problem. Nevertheless, with this approximation, we are able to write the problem in this form. Plus initial conditions, where y of t now is a vector of dimension Rd, And in particular, this is going to be something like y11, y12, yn1. I'm sorry, it's the other way around. And just follow the the natural row-wise ordering. So this is going to be y11, y21, y31, yn1. So that's the order. So then we're gonna have y21, y22, and so on. So this is the vector, how it looks like the vector, maybe transposed. All right. So once this is set, in the next lecture, we can get some simulations, and I'll go through the code that I've put in the lecture notes. All right. Thanks again for attending this class. Feel free to contact me anytime, and we see you in the next lecture. Bye-bye.